Buna bakıyoruz değil mi? Sunuyu başlat. Hadi. Şimdi küçük. Tekrardan kapatalım. Tekrar. Şimdi aynen şu bu. Paylaştım. Tamam. Sunuyu da açsan şuradan. Sunuyu mu açılıyor? Bilgi hocaya bağlamamız. Zor geldi. Büyütemiyorum ki. Ekran paylaşımı.
Bilgi hocayı şuradan bağlayalım mı?
Evet, takımdan bağlı online yapacakmışlar.
Tamam, şu an bekliyoruz onun katılmasını o zaman. Şu an gözükmüyor.
O zaman Bilgi hocayı
Tamam.
Açtırabiliriz değil mi? Buradan önce bir sayfa geçelim. Mikrofon yeterli alıyor mu? Bilgisayardan alıyor. Bu çalışıyorsa bunu yaklaştır. Çalışmıyor. Tamam.
Hocam iyi oluyor.
Tamam. Good afternoon. First of all, I want to thank the organizing committee for the invitation. I want to thank also the audience. Some of them is here and some of them are on the internet. I am going to share with you some information about metal powder production technologies. I hope that you are really going to enjoy the time we spent together in this session. Now, I want to give you a couple of words about my CV. I have graduated from the Medical Technical University Gaziantep campus in 1991, and I have graduated from the Master of Science from the Gazi University Mechanical Engineering, and I have taken the PhD degree from the Clausthal Technical University, Germany. My study subject was gas automation process in the Master of Science degree, and also some of the part of my PhD study was about powder production by using gas automation process. Now, the title of my presentation is Spherical Powder Production Methods for Metal Additive Manufacturing Process. The context includes the definitions. First of all, I want to give you some basic definitions about what is powder, what is particle. Then I will give you metal powder production methods, and then the methods used for additive manufacturing. And then there are some new methods in the literature. I will give some information about new methods, and at the end of this presentation, I will give you some challenges for powder production. According to ISO standard, the number is given in the presentation, 3252, 1999. We define the powder as a set of discrete particles, usually less than 1 millimeter in size. And we define the particle unit of powder that cannot readily be subdivided by usual separation processes. The grain term is not true for the particle. For that reason, it is stated that in the standard, the particle, the grain cannot be used instead of particle. Agglomerate is another definition. If some particles are adhering together, it is called as agglomerate. And agglomerate can be divided into particles by physical techniques. If you look at the figure, you can see one inside a particle. You can see the grain. It is a microstructure grain. For that reason, it is not true to use grain instead of particle. Number 2 is particle, and number 3 is collection of particles, and they're together. They are. It is called as agglomerate. Metal powders for additive manufacturing is the raw material. As you know, we use powders to make some parts by using different additive manufacturing processes. For that reason, metal powders is a very important element of the metal additive manufacturing process. The critical factors influencing powder attributes must be managed carefully through its entire life cycle to produce quality parts at a competitive cost. The life cycle of metal powder includes powder production, shipment, and various additive part manufacturing steps. In this presentation, I will focus on powder production methods. Powder quality and consistency needs to be maintained at each step of the process, including powder storage and handling also. The important elements of metal powder include development of physical-chemical properties, wide supply base, and competitive cost. Now, let's look at the critical factors of additive manufacturing metal powders. Spherical powders with low level of satellite. If a small particle is combined to a big particle, it is called as a satellite. For that reason, it reduces the flowability of the powder. Due to this effect, spherical powders have to without any satellite or at low level satellite. High percent reposibility level is also important. Oxygen level is also another critical factor. And there can be a porosity in the powders. It is also a factor. Good flowability is very important, especially laser wet or electron beam melting processes. High apparent and tap density, they are density definitions. There are many standards about powder properties. Some of them are listed here. For example, apparent density measurement, there is an ISO standard 3323 one. And tap density measurement, I don't want to give the detail of the measurement techniques, but there are many standards describing the measurement techniques, and it is used in this industry very much. If we look at the powder production methods, normally we can classify the powder production methods as atomization processes, multi-technique, rotating electrode process, mechanical process, chemical processes, and also it is not listed here, electrolytic processes. Powder production method controls the particle size, particle shape, and other attributes of including purity, microstructure, and cost. For the production of metallic materials, atomization of molten metals and alloys is one of the common mechanisms for production of spherical powder. Let's look at the particle shapes. If you look at a powder, in a bulk powder, you can see such a figure. If you look at in closer scale, for example, the particles are irregular in shape. It can be rounded shape, and it can be acicular shape. It is produced by mechanical process. It can be flake type, and it can be spherical. Spherical powders are used for additive manufacturing processes due to the high flowability and high densities. The production method defines the final particle shape, but there can be some operations, some irregular particles can be shaped into spherical by additional processes. Now, for additive manufacturing, mainly There are two methods, gas atomization and plasma atomization. The gas atomization has mainly two types. Can you see the mouse? No. On the left corner, it is typical gas atomization process. We melt the material in a crucible and we pour the melt through a hole and the nozzle applies a high pressure that disintegrates the molten material into small particles. It is solidified in a closed chamber, so the powder is obtained in the closed chamber. So we can control the atmosphere. For that reason, we can produce clean powders. On the left bottom figure, the IGA, electrode induction gas atomization process. It is suitable for the materials that we cannot melt the material in a crucible. For example, titanium and titanium alloys cannot be melted in a crucible. For that reason, we have to use the IGA process for titanium alloys and like such metals. There is no contact of the melt with any material. For that reason, there is no problem, and we can disintegrate the liquid melt by using a high pressure nozzle. It is schematically similar in structure. The powder production unit has similar structure, but the melting is different for both these processes. The plasma atomization, right bottom corner of the figure, it is especially has increasing attention due to the advanced manufacturing processes, and in research there is much interest for the plasma atomization process. We can produce titanium alloy powders from a solid wire by using plasma torch, and there is no contamination because there is no contact of the melt with any surface. Right upper side of the figure, only the melting is different from the gas automation system. We can melt the metal in a crucible by using plasma torch, and the remaining system is same with the gas atomization process. This right bottom figure is from our study. I have conducted a project from Civitak. It was about plasma atomization. We have designed and constructed plasma torch, and we have tried to titanium alloy powder production. Now, as I said, there are mainly two basic processes. The first one is gas atomization, and the second one is the plasma atomization. Let's look at a little bit in detail to the gas atomization process. The gas atomization process can be divided into two groups: free-fall nozzle and close-coupled nozzle. The most used systems are close-coupled nozzles because we can produce fine powders by using close-coupled nozzles. Free-fall nozzle can also be used, but the final particle sizes are bigger than the close-coupled nozzles. We can use air, nitrogen, argon, and helium gases for the gas atomization process. depending on the material, all gases can be used. But if you want to produce clean powder, we have to use argon or helium, because air includes, which is air, there can be oxidation of the materials, and nitrogen is not inert gas. For that reason, argon and helium are inert gases. For clean powder, we have to use argon or helium gases. What about the advantages? Suitable for most metals. If you can melt the material in a crucible, you can use gas atomization process for the powder production. The final particle shape can be spherical if the atmosphere is inert. If there is oxygen in the atmosphere, it cannot be spherical. It can be irregular. As a result, the powder has high flowability, high powder density, clean, and maybe the most important issue for the cost is the high production rate. Due to high production rate, the final cost is less than the other methods. There can be also some problems during the gas atomization process. We can produce spherical powders, but we produce the powder in a closed chamber. In closed chamber, there are powder clouds. Due to the powder clouds, there can be split cap, open porosity, elongated shapes, broken, agglomerated, irregular, or satellite formations on the right bottom. If you control the process parameters correctly, you can reduce the problems. Kaçta başlamıştık? Kaç dakikamız var acaba? Program ne kadar saat?
2-5 geçe kadar.
2'yi 5 geçelim.
3 dakika.
Geç başladık.
Tamam hocam. Devam edelim.
The output of gas atomization process is powder. The powder has a size distribution. If you look at the figure, the arithmetic average or mean size of the powder can be between 20 to 120 micrometers. D50 is the mean powder size. Depending on the process parameters, you can reduce the mean powder size until 20 micrometers. We have a size distribution, and we use some portion of this size distribution for laser bed production processes. It is most generally less than 53 micrometers. The range is generally 15 to 53 micrometers. If you look at the distribution data, and for the laser bed production process, let's say the powder size should be between 15 to 53 micrometers. And if the medium powder size is 20 microns, the yield can be about 50%. If the medium powder size is 60 micrometers, the yield can be 40%. The remaining powders can be used in another processes. It is listed at the above figure. For example, until 106 micrometers, we can use for EBM process. Coarser powders can be used for another powder metallurgy processes. press and sinter technology, and another techniques. The smaller powder, less than 15 micrometers, can also be used for metal injection molding process. So, if you produce a powder, it has a size distribution, and after classification, you can use each part of the classification for different applications. The left figure is from ALD, and right figure from Anas laboratory from USA. It is about aluminum powder size distribution. It has a similar size distribution for 50 to 53 micrometer powder. Yield is about 60%. So we can say that the yield for this powder size range can be from 40 to 50%. It increases the costs. Now, let's look at the titanium alloy powder production processes. We have already talked about IGA, electrode induction gas atomization process, plasma wire atomization process. Sometimes it is called as plasma wire or plasma atomization. And plasma rotating electrode process is another process. And cold wall induction crucible atomization process is another process. There is a crucible in cold wall induction process, but there is no contact between the melt and the crucible. But the energy used is very high. For that reason, it is not competitive with the other methods. Let's look at the oxygen level for some size range. If the powder is less than 50 micrometers in size, it has 3,500 oxygen in ppm. Less than 45 micrometers, it is 800, and if powder size is greater than this value, it can have 600 ppm oxygen level. We can easily say that small particles are more sensitive to the oxidation. If you look at the IGA process for the titanium alloy powder production, it was the first method for the titanium alloy powder production. Plasma atomization is now mostly used for the titanium alloy powder production. In this process, the production rate is very low. It depends on the electrode diameter. Until 90 or 100 millimeters electrode diameter, the production rate is about 1 kilogram per minute. If you increase the electrode diameter to the 140 millimeters, the melt rate can be increased until 1.5 kilogram per minute. The production rate is not so high. It is very small. For that reason, the cost is high. The plasma atomization in recent years, this process has very much interest, and many alloys are produced by using this method. The most used alloy is titanium alloys, but aluminum and other metals are also produced by using this method. Let's look at the advantage. Spherical shape, no satellite formation, because the production rate is very low. For that reason, there is no high powder cloud in the chamber. For that reason, satellite formation is less, or there's no satellite. High flowability due to the perfect spherical shape, and high powder density as a result. There is a technique, plasma spheroidization process. It uses plasma, RF plasma, radio frequency plasma. By using this approach, you can convert the irregular particles to the spherical shape. Now, I have a project about this method. We are starting to simulation analysis now. We will design and construct a plasma visualization system, and we will adapt to the gas atomization system in our laboratory, and we will try to study the effect of plasma for the spheroidization process. This process can be used especially for used powders to make spherical, and also if you have a particle from any production method and it has no spherical shape, you can convert the shape into spherical shape. There is ultrasonic atomization approach in recent years. It is a lab scale production method now. There's a tungsten electrode between electrode and substrate. There is a plasma arc. By using this plasma arc, you can convert the metal rod into powders by using the ultrasonic vibration on the substrate. It is called a sonotron. There is a vibration on the sonotron. This integrates the melted material into small particles. It can be used in laboratories. Some companies are producing such systems. For the left column, you can see all types of production methods. Top gas atomization process. There are satellites, trapped rotating electrode process. There can be no satellites. IGA also has very low satellites or no satellites, and plasma atomization. Atomized particles also have no satellites or very low satellite formations. On the right column, they are the powders. We have produced this powder by using plasma atomization process in our laboratory in Gazi University. They are perfectly spherical and very smooth surface. Okay, after this slide, I can conclude due to the time restriction. There's a new process approach. It is similar to spray coating process. There is a wire and there is a thermal spray piston. You can produce the powder by using this system. It is in 2019 in the literature. It is a new approach for powder production. It is similar to the thermal spray process. Okay. What about the challenges for powder production? Increase of production yield, cost reduction process, and quality improvements. They are the three challenges for the powder production. The first step in improving the facility is to decide which of the above needs is critical. In fact, it has the potential to improve all of them. There are many studies to increase yield, cost, and quality, because we need high quality powders, especially for additive manufacturing processes. There is always challenges to increase yield, to reduce cost, and to improve the quality of the powders. Okay, thanks for your attention. Thank you very much. What about you? There are any questions? Is there any question? No. Okay, thank you.
Hı hı.
Oradan mı buradan mı?
İki taraftan da gözükecek. Şöyle. Buyurun.
Okay.
Evet.
Oh, shall I start? Okay. Good morning, everybody. Not good morning, good afternoon. Sorry. Good afternoon. So it's a very crowded session. So thank you very much for listening, and also I would like to thank the conference organizing committee for inviting me to give this speech. Well, actually, my presentation is going to be on metal additive manufacturing, and I will talk about some of the trends, some of the opportunities, and the challenges. So it's going to be a bit informative kind of presentation, not very academic, but also I will mention about some of the research topics and also what we are doing, basically. I mean that I have a research group called Advanced Manufacturing Technology Research Group, and I have almost 20 students and some of postdoc researchers as well. And we focus on main additive manufacturing and processes and design, and also we work a little bit more on materials, not very detailed, but actually we mainly focus on additive manufacturing. So first of all, just roughly, additive manufacturing is a layer-based manufacturing process. When we compare with the, let's check my time. Yeah, we compare with the material remove process. So in contrast, we add the material, not remove the material. So therefore, we will have less waste material than the material remove process. And we use the layer by layer adding material and to obtain 3D objects. So the steps in additive manufacturing is starting with the CAD data, and we convert it to STL data, and then we slice it and get the knowledge or get the data from each layer.
and then actually we generate tool paths or scan paths or whatever for the given layer, and then we convert to the machine codes, and then we actually use a machine to produce the 3D metals, 3D sort of objects. So this is totally digitized manufacturing. So therefore, we actually pass prototyping, manufacturing, assembling, like tooling, so fixturing, etc. So for doing that, basically, in some cases, it will help us to reduce the lead times, also production times as well, in some perspective, but also actually the production time of the 3D printing is not very short. In sometimes is very long. Well, just a very, general classification is we classify the additive manufacturing processes based on the material type or material form, liquid base, solid base, and powder base. And then in liquid base, we do melting or polymerization. In solid base, we do laminated object manufacturing. In the powder base, again, we do melting or binding. And under melting, we actually mainly use metal additive manufacturing processes like selective laser sintering, melting, direct laser metal sintering, electron beam melting, and laminated engineering net shaping. But when we focus on the metal additive manufacturing, basically, we have two heat sources, beam and arc. And we use beam as coming from laser, and the other one is coming from electron beam. And arc, we use actually technique and mark or plasma arc, as well as we can use dual plasma. And afterwards, we classify metal additive manufacturing processes based on feedstock, like whether we use wire or powder. So when we use wire, when we use laser beam, so it's going to be wire plus laser AM. If you use powder, it could be process is going to be done on the powder bed, or we actually blow powder or send the powder from the nozzle, and it is going to be powder bed fusion process or blown powder bed or DAD process as well. If we use the electron beam process, we definitely use actually electron beam. So we use electron beam wire CIK. Or we can use powder again in the powder bed, which we call as electron beam melting. Well, actually, when we use the arc heat source, we have wire for WAM systems, wire arc additive manufacturing. Also, we may use dual plasma system as well to melt the material and to deposit the material and to create the 3D objects. Of course, all the additive manufacturing, they are not all same. They have some advantages among each other. Basically, for example, when we take a look at the complexity, the powder bed systems, we get the more complex structures. But when we take a look at the WAM process, so we may get the less accurate or complex parts or the products. So actually, if you can see that, for example, cost saving, the accuracy, they all change. There's no optimum process, basically. It depends which products you are going to produce and what kind of requirements do you have. So you have to select which process is going to be suitable for you. And of course, in this case, in additive manufacturing, the buy-to-fly ratio is very critical calculation, how much material we use. Well, basically, we calculate the buy-to-fly ratio by, dividing the weight of the raw material to weight of the final component. For example, if your weight of the material is 10 kilos at the beginning, and then if you get, for example, the final product is 2 kilos, so your buy-to-fly ratio is 5. So our aim is not to increase the buy-to-fly ratio, to decrease the buy-to-fly ratio. So if the final weight and the initial weight is going to be 1, this is an ideal condition. That means you do not have any waste. So that is the perfect condition, or ideal condition. But in fact, there's always some kind of chips or some kind of waste. So it is mostly bigger than 1, but if you close to 1, that's the best condition for additive or manufacturing process. So if you take a look at the metal additive manufacturing processes, You can see from these charts. So some of them, for example, some processes have high deposition rates, some processes have low deposition rates, and layer heights may change. Surface topography may change, and relative cost also may change. But also, actually, I mean, we can get more accurate surfaces or more accurate actually results. So we may have some kind of other bad sides for the process as well. And those processes, of course, I mean, the additive manufacturing process, not all of them mature, and they have some maturity level, basically. But among them, laser powder bed fusion process is now the most mature process. So commercially sold, and you can actually buy the machines, and software are developed, and so you can use easily. And then the other processes are coming to this level, but not actually that's kind of the level we reach as powder bed process. But I mean, the researchers and the companies are still working on it. But probably EBM and powder laser deposition and WAM as well is going to be going to this high maturity level as powder bed fusion process. The laser one, I mean, the laser is the main heat source in metal additive manufacturing, and actually we use laser for powder bed systems and DAD systems and wire melting wire system as well. And so we use laser for melting and depositing the material. So therefore, laser is very actually prominent equipment for us in metal additive manufacturing. But when we talk about laser, of course, the optic systems or optics are very critical. So therefore, we use optics and galvanometers or some kind of other optic systems. So these are other actually, the costly equipments, and so high cost equipments that we are using in metal additive manufacturing systems. So when we take a look at the arc, so as I said, we can use MIG-MAC arc, plasma arc, or TIG arc. Actually, the equipment for those arcs is not as cost as or expensive as laser, but we may have less actually costly products. And so therefore, we use them again for melting and deposition as well. So what is the raw material? Of course, we use two types of raw material. We use two types of raw materials. I accept this guy. Okay, yeah. So we use two types of materials, metal powder and metal wire. So I mean, Professor has already mentioned about the powder production, so I remove them all. I know that he's going to actually mention about the powder production, but we have the metal wire as well. I'm not going to explain how we produce them basically, but between them basically the cost may differ, production time, surface quality may differ, density, availability, materials diversity, and efficiency may differ depending on you use powder or wire. But in fact, the wire efficiency almost better. Or deposition efficiency as well, cost as well. I mean, the cost is going to be less, but the deposition rate is going to be high because even the powder bed fusion process or powder pad fusion processes, we lose some of the powders. But in wire, we use actually 100% wire to deposit the material and also get the the product or produced product. I just very quickly mention about the trends because the metal additive manufacturing have very high dramatic trends to up in unit sales and all the sectors and in the countries. As you can see, there is a huge trends in the metal AM systems. There is a little bit the drop in 2020, but because of this COVID pandemic. But for example, if you see the trends in AM systems and unit cells and metal additive manufacturing is still going up to actually in the sales. and mainly United States using those systems and Europe using those systems. Asia Pacific countries also using those systems very much. And how about the materials? The metal is going to be 18.2% in total, not very much as polymer and polymeric-based materials or powder as well in the filaments, because the FDM systems or some resins or the photopolymeric materials are actually sold very much than the metal, but metal is getting higher. And there is also revenue of the growth of the metals over years is getting up as well in the sales. Which materials, which metals we use in the metal manufacturing? Mainly aluminum, use 42%, titanium, stainless steel, tool steels, hassle alloys, and some inconels are mainly used in metal manufacturing, and mainly aerospace, defense companies, automotive companies, and some of the some service companies are using those kind of systems. Medical as well, medical companies are using as well. And also, if we take a look at the installed industrial systems, so the most systems is being sold in the United States, China, Japan, Germany as well. Turkey is about 1.4, not very well, but not bad, not good between them. Okay. So, what are the benefits of metal additive manufacturing? First of all, we get high strength parts. We get complex geometry parts. We may get porous structures, function graded materials or structures, smart structures. We can we can have direct manufacturing to end products, consolidated parts, high strength to weight ratio products, and we may also actually use to produce high refractory and superalloys in metal manufacturing. Let's take a look at some of the parts which are available in the industry. Some of them I took the pictures from the fairs, like Formnex or etc. And some of them I gathered from the internet. So those products, as you can see, are mainly used in aerospace applications. As you can see, they are high volume or large volume products, complex products. They can be done also. They can be produced in a single, the production, the platform. And those are mainly actually rocket science or not rocket industry. As you can see, they are also being used and developed and produced as well. On the right corner, this is the highest complex geometry and the design until now, and now it's being produced by EOS systems. And we may get, as I said, very complicated and intricate parts using metal additive manufacturing. One of them, and some of them are seen on this screen. And also we may produce large parts by using WAM systems or some laser wire systems as well. And they are used in also aerospace applications like in SpaceX or in NASA. And also, as far as I know, that Roketsan try to build such kind of big systems and big production as well. And also the manufacturing can be used for satellite parts, as you can see, for like brackets or for like some of the parts, and they're connected to the platform. So they are very complicated parts, and we can reduce the weight of these brackets from the original design as almost 50%. So let's take a look at some of the research topics. I mean, these research topics, actually the researchers, academics are still working on them. First of all, I mean, the people are working on multi-laser systems in order to increase the production time, and processing is very critical because the surface is not good. The surface also mechanical property is not actually good as well. So therefore, laser polishing, laser shock cleaning, and some of the processes are being done. And some magnetic shape memory alloys are being actually under research now. And for the laser powder bed fusion process, blended powders are being used. Function graded materials and structure are being worked by the researchers. Cold spraying is another process in additive manufacturing, are also getting famous and popular. And people try to actually produce the part using refractory alloys. And large volume production is one of the, the achievements or aim of the, especially metal system for, the companies. They would like to produce, the high volume parts as well. In steel control and monitoring, there's another research topic, machine learning, new design approach like biomimicry, and math pool characteristics, topology optimization, and phase transformation are still being actually, under research by the academics. Okay, very quickly, what we are doing as a research group. As I said, we work on metal additive mainly, one laser design for additive manufacturing, topology optimization, and we also work on the laser polishing and ECM polishing as well. Well, actually, we know that during the laser powder interaction, the matte pool is very critical. So, in one of our research work, we try to predict how much the matte pool is going to be, produced by when the laser is going to be hit on the powder surface. So we will actually develop some of the equations and some of analytical approach to get it and to simulate them by writing the computer program. And then the aim is going to be actually to obtain the good parameters or the best parameters for the the defined material. And also we work on the the materials, how the materials behave during the process, because some of the materials like titanium 6-4 actually gets into martensite very quickly, but actually during the process, if we change the process a little bit, and if we, for example, heat up the the powder beds, or if we change the parameters during the process, can we decompose the the titanium phases like alpha and beta, and we try to do some to get some parameters and change the processes to decompose those phases. And also we write some kind of programs, and we try to develop some kind of approach for laser powder bed fusion process. As I said, the surfaces are not very good, very rough surfaces we obtain in additive manufacturing. So therefore, we try to reduce them as much as we can. And one of the approach is laser. So when we apply the laser afterwards, after production, we try to remelt the surface area, very thin area, and then we try to polish it, so get the better surface. So therefore, we actually work on it a little bit. In one of the PhD students who already graduated, we work on titanium 6-4, which was produced by EBM process, and we get very good result. I mean, for example, EBM surfaces about 40 RA, we reduce them almost 2 RA by using laser polishing process. And also, some of my researchers are working on WAM. And so basically in WAM system, we develop how can we calculate the delay time, because for each layer, when we are using the WAM system, we have to wait a little bit, almost 1 minute or 1.5 minutes, especially for steel type of materials, because there's going to be a huge heat accumulation. So that heat accumulation may result some of the geometrical changes on the produced parts. So therefore, we work on it a little bit more, and we develop some kind of numerical approaches and to predict how much we need to wait for each layer in order to get the better geometries and dimensions. So we did a lot of works. We did a lot of try to evaluate and to validate. And also we work on the laser powder bed systems for the designing, that's actually for truss systems, and those truss systems, truss-based designs actually is going to be based on the density from the outside to inside. We change the density ratio, and then we actually did some of the experiments, compression tests, and how the design changes may actually result with the compression resistance of such kind of truss type of geometries. For the EBM process, we try to actually design some of the joints. I mean, and also we tried that how can we get the revolve joints, the as built cases, and then we actually use some of the designs and we actually apply them in the EBM, and then we try to determine some rules and some tolerances that to obtain the revolve joints as a consolidated design. We involved, me and also Professor Ünal also involved in a research, scientific research project, industrial scientific research project, TÜBİTAK 1511, by Ermaksan, and we actually joined a group, and then we actually developed or actually produced the first metal additive manufacturing systems. This is one of the some of the pictures are given. So now it is being sold by Ermaksan, and also powder system as well, powder production system as well. So I work with FNSS and to actually produce some of their parts by using WAM, and then actually they use it and they test it, and they now using this kind of WAM, and we did a lot of mechanical, the measurements for them, and to get the mechanical properties which are very close to their design requirements. And we also measure the temperatures and during the process, and we check the faults, and then we actually see that the isotropy of the produced parts are very perfect, not very perfect, but perfect. And also the parts are now being used by FNSS company. And I also actually work with another company, Integral Robotics, and we actually aim to develop robotic WAM systems. And these robotic WAM systems is going to be dual material feeding, magnetic table, vibration table, some offline control, and also there's going to be some kind of the measurement systems as well. So this is going to be a kind of a WAM cell. Now it is finished, and now it is actually already being presented some of the fairs, and this is some of the pictures. Now the next one, it's going to be on Formnext in Frankfurt. So we can produce very large metals and large structures using aluminum, stainless steel, steels. We haven't tried titanium and Inconel, but we successfully developed two pads. We successfully measure some of the melt pools and arcs and voltages, and as well, so we can also plot them and monitor them, so we can actually fully control the process using this cell. And also we have a lot of work on WAM systems. One of them is we try to to keep the heat around the production area. So we actually have some kind of shielding systems, and we did a lot of some of the experiments. And also we actually developed some tool pads or deposition pads, not to accumulate the heat on very narrow area. So actually, therefore, we changed the tool pads. So we did some also experiments and trials, and then we see that actually when we change the position pads based on the temperature accumulation, so we get good results on the geometry. But we're still doing the experiment, we continue them. And I work with TUSAŞ, Turkish aerospace company, to actually design and produce flight critical parts. And we did topologic optimizations, and we did a lot of measurements and experiments, and then actually successfully produced one of the parts. And so I continue. Actually, I work with TÜBİTAK Uzay to actually design a brackets. And then we use a biomimicry to design it, basically, and then we tested them by using actually, oops,